Hey everyone. So in this video, we're now going to understand how a feed-forward neural network works. In the previous few videos in this series, where we're trying to build an email classifier neural network, we have gone over the different pieces of the puzzle, right? Now it's time to put those pieces together and understand how these layers and these neurons can be combined into a network. So neural network kind of looks like what you see in front of you, right? It has a number of different layers, and you see these connections which indicate data flowing from these layers or what are neurons in these layers into the layers in front of them. Right now, the first layer typically in a neural network is called the input layer. Now, it's not a computational layer, meaning no computation happens in it. It's the layer with the inputs, right? And all that layer does is pass the inputs forward to the next layer. So it's more of a theoretical layer. It's basically when you code it up, it would just be the inputs coming in, right? But when it's represented, it's called the input layer, and it's got the data or the inputs, right, for that data point. Right? And in our case, we're just focusing on one data point, which could have multiple dimensions, right? But one data point, right? Now, if you in practice, you'd have systems where you'd have data fed in the form of batches, and the network would be vectorized, so it would handle data in those batches. But in this case, in this video, we're just going to focus on, one data point, right? Okay. Now the layers in front of the input layer are called the hidden layers, right? And by in front, I mean the next set of layers till the second last layer, right? And then the last layer, which gives you the prediction of the network, is called the output layer, as you can imagine. The layers in between are called the hidden layers, right? The reason they're called hidden layers is you know the input going into the network and you can see the prediction, which is the output of the network. You can, on paper, see the parameters and the values in the network, but it's still quite mysterious how these parameters function. It's hard to get a lot of meaning to these, the values that show up in between. All we can say is we've given it the input and we can see what the prediction is. So that's why these are called hidden layers, right? So in this case, you can see it has 3 hidden layers. Now, in this case, what we have is called a feed-forward neural network. What do we mean by a feed-forward neural network? Well, information moves in a feed-forward network from one layer to the layer right in front of it or to the next layer, right? So in this case, as you can see, it goes from the input to the first layer, the second, and so on. So there are no cycles, meaning from this point, information is not going to come back to this layer, or from where we see it is here, it's not going to come back again to, the first hidden layers. There are no cycles in a feed-forward neural network, right? And an alternative is a recurrent neural network where you would have those connections, right? You would have information coming back. In this case, the information starts from the beginning and goes away all the way to the end, to the output, right? So that's called a feed-forward neural network, and that's the kind of network we're going to be using. And a lot of neural networks are feed-forward, right? Okay. The other thing we have here is what we're going to call a network, a multi-layer perceptron network. Why are we calling it that? Well, each neuron in our case is basically a tanh neuron, which, as we know, is the input coming in, has got the linear part with the weights and the bias. So that effectively is computing, a form of averaging of the inputs. And then we're passing it through a tanh function. So this model, this kind of linear plus an activation function is considered to be a perceptron model, right? Based on the original, first kind of neural network, or which was built off what were called perceptrons, right? Simple neurons. So this is going to be called a multi-layer perceptron network, right? You could have other kind of layers. You could have convolutional layers used for images. You could have the transformer, which is used for language models and so on. And then the third thing the term we're going to learn is what are called fully connected layers. So why are these called fully connected layers? Well, you can see here that each neuron in, say, layer I, let's call this layer I, is connected to every neuron in the next layer, right? And so those layers are called fully connected. So we can see here this neuron is connected to each of these. This neuron is also connected to each of these, and so on. So in that case, it's called a fully connected layer. In our case, every layer is fully connected, right? Each neuron in the previous layer is connected to every neuron in the next layer, right? Okay. So our problem we're using in this series to try and understand how classification works and how a neural network works is building an email classifier, right? So we're passing it emails, or rather the title of the emails, and we're trying to understand if we can classify it into different classes. Now, when we implement this, we're actually going to make it slightly more complicated and have 6 classes. But for the case of visualization, in our case, we're going to actually make it have just 3 classes. And we're going to use a reduced version of the input as well, input vector as well. So a quick glimpse at what we'll end up building in the next video, which will be our final kind of finished email classifier. And we'll be using Streamlit to actually make it an app as well. So you can kind of visualize what's happening. Okay, so to give you a quick glimpse, this is kind of what we'll end up, building in terms of a quick UI as well at the end after we've trained our net. So you'd have, the ability to enter your email here, and then when you say add email, what it would do is actually go and, run the, send this to the neural net which we have trained, and then you'll see that that email has been added here and it has classified it into work, whereas we've not specified what the email is, right? And you're seeing other examples here of emails, or you can call them email titles that we are sending in. You could actually give bigger passages as well, and you'll see how it works, and you can test the model. And so obviously this app has been built with Streamlit, but then it's underlying that we're actually using the network that we have trained, right? So it's an example of how more complex apps can obviously be built, and this is what we'll end up doing in the next video. So coming back to the slides. So the first thing, and we have covered embedding models in the previous video actually in a fair bit of detail. You should have an understanding how they work at least. We're going to take this, you can call it the email title, and using a sentence transformer, compute it into a vector embedding. But in our case, for visualization, you can think of it as then using a principal component analysis to make it a 2-dimensional vector. So each email, for our case, let's say it becomes a 2-dimensional vector. So this email mathematically is equivalent to 0.3 minus 1.3. So now let's kind of construct visually, right, a neural network. And this whole video, we're going to visually understand how the whole process works, right? So by the end of this, you should have a very good understanding how a neural network works, and the basic idea behind its tree. Correct. So you have this email, it would be converted into this vector embedding, and that is our input layer, right? So the input in this particular case would show up. Now, what we're going to have is 2 hidden layers, and it's a simple, problem. In this case, we have a small input size. So 2 layers suffice. The first layer is a 2x3 layer. What do we mean by that? Well, it's got 2 inputs coming in and 3 outputs. What do we mean by 3 outputs? It means for a multi-layer perceptron, it's basically got 3 neurons, right? And then the next layer is a 3x3. So you have 3 neurons and it's 3 inputs coming in. Now, one thing to keep in mind when you create a network like this is the compatibility of dimensions, right? So if it's got 2 inputs, then this dimension has to be 2. It should be, each neuron should be able to take in 2 inputs, which means it needs to have the corresponding number of weights and the bias. It's got 3 neurons, so it's 3 outputs, which means the next layer, in this case, this one should, for it to be fully connected, each neuron should be able to now take in the 3 outputs from here. So it should have 3 weights and a bias. And then, it's giving out the 3 outputs. And then the last is the softmax, which, as we know, will take out, the prediction from the hidden layer, which is in the form of logits, right? So they're just values, and it would convert them into probabilities. So at the end of it, you will get a prediction of what class the email belongs to. In our case, we're going to have 3 classes of categories. We're assuming the email can either be spam, can be marketing, or it can be important, right? And in our final example that we'll implement in the next video, we'll have 3 more classes. So it'll be 6. But in this case, this is good enough for visualization. So the next thing we need to do is now understand the parameters of the network. So you have the neurons in these layers. Each neuron has, for a multi-layer perceptron, the weights and the biases. How many weights does it have? We know this from the lectures previously where we have covered the neuron and layer, but a quick recap. 2 inputs coming in from the previous layer. So it needs to have 2 weights, each corresponding to each input, right? So the W11 indicates it's the weight connecting, or on this line, right, connecting the first input to the first neuron. And the W21 indicates it's the weight connecting the second input to the first neuron, right? And then 1 bias. This is 1 indicates layer 1. So now this layer, every neuron will have its own weight and bias. You can see the nomenclature is slightly different, right? It indicates, the second index indicates which neuron it's connecting to, and the first indicates which neuron it's connecting from. In this case, slightly different. It's getting three inputs, right? Each neuron here is going to be passing its output to this. So it's going to have three weights, one associated with each neuron here, and one bias. And that's the same for the three. And these are the parameters of the neuron. Then you have the softmax, which is just, as we know, is just a functional layer. It's just a function. In our case, no parameters. So let's initialize this. How are we doing that? So if you already have a pre-trained network, something that works, even if it's for a slightly different problem, but you know it's helpful, you can start with those weights. In our case, we're just randomly initializing this. So in our case, let's say for this neuron, the weights are 0.3, 0.1, and the bias is 0.7. And similarly, we have that for the other. And in this layer, again, we've initialized these weights. I've come up with these randomly, but I've also trained this network, so I know that these actually are good enough initial points. Sometimes you have an initial point where the training does not work, and you might have to kind of restart from a different initial point, right, or initial set of parameters. So now let's do the forward pass. So first layer, A is the output of the layer, A0 is the output of the first layer. It's the input layer. So what is passing to the next layer is just the inputs, right? So A0 is X. Now what does it do? It passes that to each neuron in the layer. And as we know, they are tanh neurons. So how they work, the output of the neuron, A1, which is the output of this layer, right? I'm just writing the notation layer-wise. So you can then, kind of understand how it works for each neuron. But we've covered the neurons and the layers in a lot of detail in the second and third videos in the series. So you can just go back and refer to that. Is basically sigma I, Wi, and in this case, it's output of the first layer. So it's taking the input of the previous layer. So Wi Xi, which in this case is Wi Ai layer 0 plus B. So these two would pass through this. You can evaluate this. You have the inputs, you know the weights, which I've shown you previously, and you should get this. The second neuron and for the third neuron. And that's the layer, right? You've got the outputs for the layer. Now we evaluate for the next layer. So now each neuron here is taking in the inputs from the inputs as the outputs of the previous layer. So A1 is what's coming in. It's going to have its own weights. So I haven't used the indices, keep the notation clean, but it's going to be the weights of each neuron itself. And you're going to get the outputs of the second layer. So you get that, you get the outputs of the second neuron and the third. Now what happens? These are the logits that it's predicting, right? But to make a little more sense of this, we want to convert it into probabilities. So that gets fed into the softmax, which, as we know from the lecture on softmax, is basically this function, right? And it's going to, so I'm not going to go in detail. Please go and refer to that lecture if you're confused, and we go through that in a lot of detail. But the softmax, as you can see, takes these and converts them into probabilities. So what does that tell you? It tells us that there's a 0.36% that the email is spam, the 0.29% that the email is important, is marketing, and a 0.35% that the email is important, right? And this is the prediction. So it's SI indicating the output of the softmax. I'm trying to be consistent with the previous videos in the series. And the output of the network is typically referred to as Y hat. So Y hat is SI. So you see this prediction. Now, what do you notice kind of when you look at this prediction? Think about it for a second. So we see that the predictions, because we have just initialized with random weights, the network is functioning, but the predictions kind of are confusing, right? Like it does by a 0.01 kind of tell you that the email is, this. And when I say 0.36, it's 36%, 29%, and 35%, right? It's fractional, right? So it's in percentage, it would be 36.25. Said that wrong just a second ago. So it isn't very clear. You can see that the network is kind of not doing a great job, right? It isn't completely clear. It should clearly indicate that the email is spam. We know it is. It's the email saying you get a free smartphone, right? And the other probabilities should be much lower, right? But in this case, that's not the case. So the prediction is clearly not very, accurate. It's a bit confused. The prediction should be a lot more clear, right? So in this case, it should very clearly indicate that the email is spam. And the other two probabilities, it's hard to make them zero in practice, but they should be fairly low, right? So what do you do for that? Well, the answer is simple. That's why the neural network is trained. And what are you training, or what do we mean by training? We're trying to find the best set of weights and biases, meaning these parameters, such that for our data set, the neural network is able to accurately predict, clearly, what kind of email it is. And then we hope that if it can do that for our data, then in practice, it's going to do the same. So the weights and biases of the layers have to be trained. So the first thing, how many parameters do we have? So first neural network, first layer, it's got, two weights and a bias, and there are three such neurons. So 3 times 2 plus 3 is 9 parameters. Right? The second one, you've got 3 weights and a bias per neuron. So 3 neurons. So it's 3 times 3, right? Which is this 9 plus 3, which is 12. And so in total, we have 12 plus 9, 21 parameters, a very small network, right? If you were training a much larger language model, you'd be in the millions or the billions or trillions of parameters. And in practice, when we do this in the next video, we're actually going to have, close to 20,000 parameters, much more complicated. Okay. So we've got the parameters. What else do we need? Well, we have a data point, right? And we have the vector version of it. What we need is the category or the class label, right? So we're saying it's spam. And in our case, the way we have ordered it, spam is one, 2 is marketing, and 3 is important. So class 1, which means we're going to use what is called a one-hot encoding, right? But to convert this into a vector, because the softmax is giving us probabilities, we need to kind of give it something that can be compared. We are giving it a set of probabilities. And because the label is, the exact answer, we're saying the probability is 1, that it's spam, and 0, that it's not the other classes. And we've covered one-hot encoding in the video on cross-entropy loss. So we've got the one-hot encoding. What we need, as we said, is the loss function. The loss function is a way of calculating the error in the prediction, right? And so the output of the network feeds into the loss function, so does the label. So you have this probability distribution going in from here, and this going in from here. And y hat is the prediction, y is the label. And the cross entropy loss is this function. It's going to, and we've covered this in a lot of detail in the previous videos. It's basically going to take, yj log y hat j, and the sum of that for each j. So it's basically, in this case, if it's 100, 1 times 1 times log 0.36, and then 0 times log 0.29 plus 0 times log 0.35. It's going to sum that and then do a minus of that, right? And that's the loss. So in our case, it's taking these two distributions, and the output you get is 1.05. So 1.05 is the loss or the error in the prediction. Very good. We know how bad the prediction is in terms of a number. What do we do next? We need to train the network. What do we need? We need the sensitivity of the loss with respect to the weight and with respect to the bias of each of these neurons, right? So I'm just using this notation generally. It means with respect to each. So how do we do that? Well, the loss function, you have a sensitivity associated with that. So you can compute the sensitivity of the loss function with respect to the inputs to the loss function. We don't care about the input to the label. We are computing the sensitivity of the loss with respect to the inputs from the softmax. So S is the output or the prediction of the softmax. You can also call it y hat. And we want a sensitivity to the loss with respect to that. And we know how to compute that for the cross entropy. We've covered it previously, right? So we get that value. And typically when the softmax plus cross entropy is used, you can compute the loss actually directly with respect to the inputs of the softmax. But for now, let's just say we get this. And then we do what is called backpropagation. And so we use chain rule of differentiation to now take this sensitivity, which is the sensitivity of the loss with respect to the output of the softmax, push it through this, and get the sensitivity with respect to the inputs of the softmax. And we can, as I said, you can do that directly with softmax, but we have to do this for each layer. So the derivative with respect to the output of the second layer is basically using chain rule, the sensitivity for each component. So each output of each neuron is sum of, this is the chain rule. And we've covered this again, the sensitivity of the loss with respect to each output of the softmax times the partial, which is the sensitivity of the softmax, the partial of that output with respect to the input, right, coming into the softmax. So we can evaluate this and we end up with this. So now this is the sensitivity of the loss of this with respect to the outputs of this layer. We have kind of backpropagated through the softmax layer, right? And the softmax has no parameters, so we don't need to worry about any other sensitivity. Now it becomes interesting, right? So now we need the sensitivities here. What we're going to do now is backward or back propagate through this layer. So what do we have? We have this layer has weights and the bias, and we need the sensitivities with respect to that. So same kind of basic formula, chain rule. The sensitivity is coming in that the softmax is giving you in the backward prop. And then the local sensitivities, the dou AI, the sensitivity, the output with respect to the weights, right? We already know that analytically for each neuron. Use the chain rule like before, and you can propagate back through this. So you get the sensitivity of the weights now with respect of the loss with respect to the weights of the neurons. And I've shown you that for the first neuron, but now you have that for all the neurons, right? And again, you can go back to the third lecture in this series where we do that for a layer. The second lecture, we cover that for the neuron. So the math is kind of covered there. This is just to give you an understanding of how the system works, right? We've got this, and so we've got the sensitivities of the loss with respect to one set of parameters. What else? Well, we now need to backpropagate through this, right? Because we also need the sensitivities with respect to the parameters of layer 1. So now what do? Well, we get the sensitivity with respect to the outputs of layer 1, which are the inputs to layer 2. Now it becomes interesting, right? You have 3 neurons. So each neuron, in this case, for this neuron, you will get the dou L, dou AI, because each of these outputs of this neuron go into each of these neurons. So this will give you dou L by dou AI, meaning it will give you the sensitivity with respect to this neuron, and this neuron, the outputs of those neurons. Using chain rule, same principle. This neuron will give you the same, right? It will give you the sensitivity with respect to these 3. And then this neuron will give you the sensitivity with respect to the outputs of these 3. Once you get that, you kind of sum them up. You can either pass them individually through, do the backprop and sum it later, and sum it parameter for the parameters. But what we can do is for that layer now, this is the contribution. We sum that up, and now what we have is the sensitivity of this, the outputs, or sensitivity of the loss with respect to the outputs of this layer, A1. And we can then pass that back. So this value is the sensitivity with respect to the output of neuron 1, it goes there. This value is the sensitivity with respect to neuron 2, it goes there. And this value is the sensitivity with respect to neuron 3, it goes here. Right? Typically, these calculations would be done at a layer level using matrices in practice. So the whole layer value would have been computed in one shot and would have been passed back. Right? But visually, just to understand how it works. So now we're down to this layer. Same principle as we did with layer 2. Compute the sensitivity with respect to the weights here using the chain rule. The outputs which we have just computed. So we've got the sensitivity of the loss with respect to the outputs of the layer. Use chain rule and the local derivatives. We have the sensitivity of the output of the neuron with respect to the weights. Use the chain rule and we get the sensitivity of the weights. So I've used green here to indicate the sensitivity of the weights, right? And so we've got that. And that's it. You don't need to pass this further back because these are the input, or this is the input layer. If there was another hidden layer, you would have to propagate through that, like backpropagation. So that's that. We've kind of understood backpropagation as well. I'll add links to lectures on some of these, including backpropagation as well, and more examples of neural networks that we have done as part of other videos. So if you want more practice, you can kind of go look at them as well. But what we've got at the end is these sensitivities, right? We've got the sensitivities of the weights and bias of both these layers of all the. What do we do next? Well, first thing, what do you get from the sensitivity? So let's take this first set of sensitivity. Right? What does it tell you? Well, the sensitivity, first of all, is with respect to the loss of the network, right? And so what it tells you is if the value is positive, it tells you that when the weight, the parameter is increased, the loss increases and vice versa. What we want to do is decrease the loss. So what you have to do is reduce the weight value. On the other hand, if it's negative, what does it tell you? It tells you that when you increase the parameter, the loss comes down. So you need to go in the opposite direction again. So that's what the sensitivities imply. They tell you in what way you need to change the weights so that the loss comes down. In this case, you will have to decrease this, and you might have to increase this, right? How's that done? The first thing you do is take all these weights and biases and put them into a vector. So this is here, and so on. Make it in a vector. And so it becomes the gradient vector, right? Which is basically the gradient of the loss with respect to each of these parameters. And then we use the gradient descent algorithm. So you have the weight at a particular iteration, right? You start with iteration 0, in our case, initial guess. You have what is called a learning rate, which is set. We set it, and it can be dynamic, but for now, assume it's constant. And you have the gradient you've computed. And you say, well, in the next step, the weight is this minus the learning rate times this gradient. So in our case, this minus 0.01 times this. Why are we using minus? It's gradient descent. We know that if the sensitivity is positive, increasing the weight increases the loss. So we want to decrease it. We go in the opposite direction. We decrease the weight so that the parameter changes. We do this for, say, the first data point, and you get a new set of W's. You evaluate the network again, do the forward pass, do the backward pass. You'll now get dou L dou W for that iteration. So this is dou L dou W I. You get the dou L W for that iteration and do this again. And the weight will change again. You can keep doing this iteration after iteration. Now, if for each data point, you kind of update the weight. So in this case, we've seen one data point, right? We had the 0.3 minus 1.3. If you compute it for that, and then you update the weight, it's called stochastic gradient descent. For each data point, you're constantly updating the weights, which is a very quick way because you're going to if you have 1,000 data points, you've gone through 1,000 updates. The problem is that it can lead to oscillations in your convergence of the weight, right? And we've covered this in a lot of detail in our video on gradient descent. It's actually 3 videos on that, and it's a lot of detail. So I'll add links to that. But basically, stochastic gradient descent, while it seems very quick, can lead to convergence issues. So typically what is done is what is called batch gradient descent, where what you do is take a batch of data points. So we have this, but we have a few more. For each of these, you can compute the sensitivities. And then what you can do is, let's say it's a batch of size n, you can average those sensitivities. So now, if this is probably saying increase the weight a bit, and this is saying decrease the weight a bit, and so on, it averages that. And then that is the dou L by dou W that you use in the gradient descent algorithm. So that's called batch gradient descent. What that means is the convergence is a lot smoother because it's averaged, right? So typically, even though you're kind of taking a step, in the optimization process, only after going through a few data points, in general, it's quicker in terms of convergence and smoother because the oscillations are avoided, right? It's kind of, cleaner way to converge. Okay. So in our case, we've used a batch size, of I think 150 or 190 data points, right? Which is pretty much our data set, right? We have a very small data set, so we've used almost all of the data to converge this, and we see how cleanly it converges. Now, this is obviously for a simpler problem, but we see that the loss kind of goes down quite a bit early on in the first 1,000, 2,000 iterations, and then starts converging because it's kind of getting to a point where with that kind of model, you can't do a lot better. Now, how do you change this? You could have a slightly different model architecture, try out different activation functions. You could start and you could kind of play around with the optimization parameters. But I think in this video, we get the basic idea, right? We've got an understanding of how this works. So at this point, at 7,000 iterations, you have a solution or a set of weights that should give you a much better prediction to what you had here. So let's see what they are. So after training, we see that now the neuron weights are something like this. As you can, if you remember even slightly, the values were significantly different from what they were before. Let's do a comparison. So you started, say, for this neuron with 0.3, 0.1, 0.7. You ended up with 0.75, minus 2.91, and minus 0.81. Similarly for the other neurons. And similarly, for the second layer, you see the same thing. So what does this really tell us, right? That's the kind of issue with neural networks. It's very hard to intuitively understand what these weights are. There's a lot of good work happening, especially for image and language models to try and decipher what's happening at the layer, what feature it's capturing. But in our case, it's hard to understand. It's just the way, the neural networks fitting our function. What we do see is the prediction is significantly better. So now with those weights, you see that it clearly indicates that the email is spam. It's got a 71%, or with a 71% accuracy, it's saying it's spam, and the other two probabilities are much lower. So clearly the training is working, and we can see this for other, the other emails as well. We'll see that when we actually train our network, and we'll start seeing which emails it gets right and which wrong. We'll also, in the next video, explore, as we implement this, a little more detail on the optimization process and the parameters. Right? But the basic summary we see is we're able to build a neural network. Simple example, kind of more for visualization, but we see what the idea of the network is, how the layers work, how you can train the network using gradient descent, and how you can start with something that doesn't do a great job for our problem of interest and get to a solution that actually does a fairly good job of predicting, performance of, email class. In our case, predicting whether the email is spam, important, or marketing, right? Um, and so hopefully that has given you an visual or an intuitive understanding of the idea of a feed-forward neural network specifically, but in general, neural networks, what they are, how they work, you know. If you want more examples and you're interested a little more in the nitty-gritty, in the math, of course, we have layer level and neuron level math covered in the previous videos, but we have covered, in the deep learning from scratch series, implementing a full neural network, which is slightly longer kind of video. And in that, we have multiple examples and kind of I go through the math in significant detail. Like I look at each calculation step by step. So if you really want to revise your math, have some more practice, do go check that out. And I'll add the link to the description. And so now what we're going to do is the fun part. In the next video, we're going to first train our network for the actual problem, right? And then we're actually now going to build something like this, where you can enter your email and you'll see if the neural net can classify it fairly well. And we're seeing here that it initially, at least from what I can see, seems to do an interesting job. So stay tuned for that one.